Hello everyone, so for today's video we will be discussing Taylor series of expansion. So basically, Taylor series plays a vital role in numerical methods because it can be used to predict the value of a function at one point in terms of the value of the function and its derivative at another point. So we have here the Taylor series expansion formula, which is the summation of all the derivatives, and we have here the first functions substituted by a certain value or certain point. We also have the first derivative multiplied by x minus a, and we have the second derivative multiplied by the increasing power of our x minus a all over the factorial of how if of the expansion, and so on and so forth. So similarly, we have f of xi plus 1 is equal to f of xi plus the first derivative multiplied by xi plus 1 minus xi. So basically, it's just the same with the first one. And also, this is also the same here. We have f of xi plus 1, and all the xi plus 1 minus xi are just substituted by h. So basically, these formulas are the same. So to avoid confusion, you can just use any formulas that you are preferred or do you prefer. So for the zero order approximation, we have here the formula f of xi plus 1 is equivalent to f of xi. And for the first order approximation, we also have here f of xi plus 1 is equivalent to the first to the result of the first function added by the first derivative multiplied by xi plus 1 minus xi. And for the second order approximation is also the result of the first or the original function plus the first derivative and the second derivative. So assuming there's an nth value or nth order, so that's the time we will be applying the Taylor series of expansion that we have earlier. So for example, we have used zero order through second order Taylor series expansions to approximate the function f of x is equal to 7x squared minus 6x plus 1 from xi is equal to 2 with h is equal to 1, that is, predict the function's value at xi plus 1 is equal to 1. So in solving the problem, we have at n is equal to 0, or at zero order approximation, we have n is equal to 0, f of xi is equivalent to f of 2, since our xi is equivalent to 2, so meaning to say we'll substitute xi by 2, and for the function we will be replacing or substituting all the values of x by 2 as well. So we have 7 2 squared minus 6 times 2 plus 1. So if you calculate this one, or if you solve the value of this one, this is equivalent to 17. So that being said, from the zero order approximation, we have f of xi plus 1, that is equivalent to f of xi, right, from the zero order approximation. And we know that our xi, or f of xi, is equivalent to 17. So meaning to say this is also equivalent to 17. Now f of xi plus 1, or xi plus 1, has the value of 1. So meaning to say we'll just also replace that 1 by f of 1. So we have equivalent to 17. Now for the first order approximation, we'll move on to the first order approximation, or n is equal to 1. So we have the first derivative of our function is equivalent to f prime of 2 that is equivalent to the first derivative of our function. And if you just see this one, this is a basic derivation, and we know that the first derivative is equivalent to 14x minus 6, right? Now, if you substitute all the values of x by 2, so we'll get 14 times 2 minus 6 That is equivalent to 22. So for the first order approximation, we have f of xi plus 1 is equivalent to f of xi, the original result of the function, plus the first derivative. So we have f of xi multiplied by xi plus 1 minus xi. Now, if you substitute the values that we have earlier, we have xi plus 1 is equivalent to 1. So that is f of 1. And then f of xi, we have here, f of xi is equivalent to 17. Plus f prime of xi, which is this one, 22. So we have 22. Then f of xi plus 1 or xi plus 1 is equivalent to 1. As you can see here, minus our xi, the value of our xi, which is 2. So again, you'll also have to plug that in our equation. So this gives us f of 1 is equivalent to negative 5. Now, since we are looking for the second until the second order Taylor series expansion, meaning to say we'll continue the same process for the second order. So at n is equal to 2, so we have f double prime of xi is equivalent to f double prime of 2. And from the first derivative, we can get the second derivative. So 14x minus 6, the second derivative of this one is only 14. So there's no need to substitute any value since we have no variables anymore. So that being said, f of xi for the second order derivation or second order approximation plus 1 is equivalent to f of xi plus f prime of xi multiplied by xi plus 1 minus xi plus our second derivative, which is f double prime of xi multiplied by xi plus 1 minus xi squared all over 2 factorial. So from that, we can already substitute all the values that we have. So again, we have f of 1 is equivalent to 17. Our f of xi is equivalent to 17. And our f prime of xi is equivalent to 22. And xi plus 1 minus xi is equivalent to 1 minus 2 plus our f double prime of xi, which is 14, multiplied by xi minus xi plus 1 minus xi, so we have 1 minus 2 squared, and we have the 2 factorial. Now, if you calculate this one, this is equivalent to 2. So meaning to say, the expansion series or the answers that we have, the xi plus 1, these are the answers that we get. So these are the approximation of the functions that we have. So another example we have here, use zero order through second order Taylor series expansions to approximate the function f of x is equivalent to ln of 3 plus 4x from xi is equal to 0 with h is equal to 1. That is, predict the function's value at xi plus 1 is equal to 1. So the same process as what we did from the previous example, we also need to find the zero order through second order expansion of our function. So we have at n is equal to 0 or at 0 order expansion or approximation, we have f prime of, f of xi is equivalent to f of 0. Since our xi, the value of our xi is equivalent to 0, so we also need to substitute xi by 0. And meaning to say, we also need to substitute all the values of our x from our original function by 0. So meaning to say, we have ln of 3 plus 4 times 0. So if you calculate this one, this is equivalent to 1.099. So in this case, we need to get, or we need to write the 3 decimal places. So in this case, we have 0.99. And that being said, f of xi plus 1 is then equivalent to f of xi for the 0 order approximation. And since our f of xi is equivalent to 1.099, so we also need to substitute our xi plus 1 by the given value, which is equivalent to 1. So we have f of 1 is equivalent to 1.099. Now, we already have our function's value at xi plus 1. So is equal to 1, so we already have 1.099. So now we'll move on to getting the first order approximation. So at n is equal to 1, or by the first order, we have f prime of xi is equivalent to f prime of 0. So we need again to find the derivative of our ln3 plus 4x. So from the differential calculus subject that you had, ln of 3 plus 4x is equivalent to, the derivative of this one is du over u. So we have derivative of our u, which is 4, and then our u, which is 3 plus 4x. So meaning to say, this is now our first derivative. So that gives us 4 over 3 plus 4x. Now substituting again the values of x by 0, so we have 4 all over 3 plus 4 times 0, which gives us the value of 4 thirds, right? Now, after we got that, we also need to find the f of xi plus 1. So we have f of xi plus 1 is equivalent to the first result of the function. So we have f of xi plus f prime of xi multiplied by xi plus 1 minus xi. So substituting all the values that we have f of 1 is equivalent to our xi, or f of xi is equivalent to 1.099 plus our f prime of xi, which is 4 thirds. And then we also have 1 minus 0. So this gives us the result of 2.432. Now we already find the first order approximation. Now we move on to finding our second order approximation. So at n is equal to 2, for the second order approximation, we have f double prime of xi is equivalent to f double prime of 0. And again, we need to find the second derivative of this one. So in this case, the second derivative of this one is negative 16 over 3 plus 4x that is enclosed by a squared. So, meaning to say we have negative 16 over 3 plus 4x squared. And again, substituting the value of x. So we have negative 16 all over 3 plus 4 times 0. Then we have the squared. So we have this one is equivalent to 16 all over 9. So we already have our f double prime of xi. And then finding our f of xi plus 1, so we have f of xi plus 1 is equivalent to the original value, which is f of xi, plus f prime of xi multiplied by xi plus 1 minus xi plus our second derivative, which is f double prime of xi multiplied by xi plus 1 minus xi. And again, this is raised to 2 all over our second factorial. So substituting all the values, we have f of 1 is equivalent to 1.099 plus 4/3 times 1 minus 0 plus our second derivative. We have, so this, since this is negative, so meaning to say we'll also have to put this as negative 16 over 9 multiplied by 1 minus 0 squared all over 2 factorial. So this gives us f of 1 is equivalent to 1.543. So meaning to say we already got the expansion formulas or expansion values of the zero order through second order series. So we have, for the zero order, we have 1.099. For the first order, we have 2.432. And for the second order, we have 1.543. So those were all the discussions that we have for Taylor series of expansion. And I hope you learned something from this video. And I'll see you on the next video.